Hello and welcome. We are starting another course, all right, which is shear force and bending moment. So, for you to fully grab the concept of this course, kindly click on the link displaying on your screen. The link contains of our past lecture on beam. So there we have talked what a beam is. I've talked about type of beam, type of support, and we have done a lot of calculation on how to calculate the reaction at the end of a beam, be it simply supported beam, be it overhanging beam, be it cantilever beam, be it a beam that is pinned, and be it a combined beam, and so on and so forth. All right, so for us to understand this, what a shear force and a bending moment is, I'm going to draw a simple supported beam to explain this concept. All right. This above beam, if it is loaded at the center, W, let's say this is the center, it's loaded, and this is a simple supported beam. I have support at both ends. So we'll just be drawing the free body diagram. Let's use a reaction, arrow subscript A, and arrow subscript B, and arrow subscript B. All right. So, okay, let's take the length of the beam to be L. All right. All right. So, if this beam is loaded as this at the center, two things can occur. Two things can happen to this beam. The first thing is this: the beam can shear at the center. That is, can break. The beam can break into two parts, and the other thing that can happen is the beam can bend. The beam can bend. All right. So it can either shear at this point, or can bend. Can bend like this. All right. So what then is shear force, and what then is bending moment? All right. So let's start with shear force. All right. So shear force is defined as the algebraic sum of forces acting either to the left or right of the section of the. All right. Now, this is the definition of a shear force. It's defined as the algebraic sum of forces. The reason why we use algebraic sum of forces is it is possible for us to have more than two load, that is more than two force acting on the beam. Here, in this case of this simple supported beam, we only have a load acting on the beam, which is just W. And we said it is the algebraic sum of forces acting either to the left or right of the section or on the beam. All right. So the if you want to calculate the shear force on this beam, the trick I use is this, very simple. If I want to calculate the shear force on this force, by the time you stand, the first thing you do is this: you calculate the shear force on point B, then you calculate the shear force at this point, then you calculate the shear force at this point. Every point that you have load, you have a shear force there. All right, so for us to calculate the shear force, we are going to be using a sign convention. I'm going to use a sign convention. You can either say let your upward force be positive and your downward force be negative, or you can say let your upward force be negative and your downward force be positive. But I always stick to one sign convention. I always go with my upward force to be positive and my downward force to be negative. So both for my moment and for the shear force. All right. So if I want to do that, I'm just going to stand at point B. For me to calculate the shear force at point B, I'm going to start at this point. Then I'm going to start at this point B. Then I'm going to look towards my what? My right hand side. So the question is, do we have any other force at this side? The answer is what? No. So the only force we have at this side is just what? Is just RB. So the shear force at point B here is going to be what? It's going to be RB. So if I take my upward force to be what? To be positive. So the shear force at point B is going to be what? Positive RB. All right. So if I want to calculate the shear force at this point, let's say the center. This is C, right? This is center C. So the shear force at C, at the center, is going to be equals to, again, I'm going to start at this point C, then I'm going to look towards the right hand side again. How many force do I have here? I have one force at this side and I have another force on what? On C. So it means I have two force. And don't forget, our sign convention is what? Upward force to be positive and downward force to be what? Negative. All right. So it means we are going to say RB, which is positive, minus what? Minus W. So here we are going to have R subscript B minus W. All right. So the shear force at A now, the shear force at point A, the shear force at point A is going to be what? If you start at point A here, how many force are you going to see? We have this, and a downward force at point A. We are going to have 3 points. 3 forces, so which is going to be RB minus W plus what? Plus RA. So we are going to have RB, R subscript B minus W, then plus what? Plus R subscript A. All right. So this is how to go about calculating shear force on this what? On this beam. Please, I want you to stick with this rule or with this form of doing this, because I've seen so many textbooks that we tend to draw a section. They will tend to take a section either to the left or to the right. But I observed that method might be a little bit confusing for us. So that's why I just come up with this method. Upward force is positive, now downward force is negative. So if you stick to this law, you always arrive at your answer quickly, and you will not be confused. All right. So now, the next thing we are going to be looking at is what? Is bending moment. All right, bending moment. All right. So what is the definition of bending moment? So for you to just define your bending moment, the only thing you just need to do is just to replace the definition that we have here with moment of forces. That is just it. You don't need to memorize and cram. No. So for me to write, I'm just saying this is defined as the algebraic sum of moment of forces. Algebraic sum of moment of forces acting either to the right or left of a section That is if you take a section, or you can say B. All right. So now, if you are asked to calculate the, if you want to calculate the bending moment on this beam here, how do you do that? Now, I'm still going to stick to this sign convention. Now, I'm going to use this upward and this downward force here to explain the concept of what bending moment, or how to take the moment on a force. All right. Now, look at this. If we have an upward force here, and if we want to take moment about point A, if I want to take moment about point A, take note of this. If I want to take moment about point A, so let's take moment about point A. So you are going to say the summation of moment about point A is equals to what? 0. That is, we are standing here and we are taking our moment, right? All right, so for us to take our moment about this point, we have two things here. We are going to start by taking our moment about point what? We are going to start taking our moment about point B, then we take our moment about point C, then we take our moment about point A. Let's start taking our moment about point B first. All right. Let me not just put 0 there for you. I need to explain every concept. All right. So if I start at point B, you know, from the concept of moment, we know that moment is defined as what? Force multiplied by what? Perpendicular distance. There must be a perpendicular distance for us to have what? Moment, not just force times distance. All right. All right. So if I stand at point B here, I only have an upward force. All right. So let me explain the concept for us. If I have an upward force, this force is going to, if it's acting on this beam, is going to push this beam to this direction, right? So this beam is going to be acting this way. So if you want to take your moment, you observe that this upward force is causing what? You can see is going to be going in this direction, right? And this direction you are seeing is what? Anti-clockwise. So this upward force is causing what? It's going to be causing an anti-clockwise moment on this beam. So if you take your upward force to be positive, it means your anti-clockwise moment too must be what? Positive. Take note of that, please. If you are taking upward force to be positive, it means anti-clockwise moment too is going to be what? Positive. And this downward force is going to be causing what? Is going to be causing a clockwise moment. So, and we are taking our downward force to be what? Negative. So it means that our downward force too is going to be causing an anti-clockwise moment. Sorry, please. It's going to be causing a clockwise moment. So if our downward force is negative, it means our clockwise moment with this condition is going to be what? Negative. Take note of that, please. Very important. All right. Now, so if I want to take my moment about point B, the first thing I'm going, if you want to take your moment on a beam, you are going to take moment about all the points. All the point that we have load. All right. So let's take our moment about point B. If I start at point B here, the only thing I have at point B here, don't forget we are looking at the what? At the right hand side. The only thing I have at point B here is just my what? My upward force. That is the reaction, RB. So if I look at this side, there's no distance. The only thing I have is just a force, which is what? A reaction, which is what? RB. So, and from the definition of moment is what? Force times perpendicular distance. We don't have any perpendicular distance, right? So it means that the moment about point B is going to be equals to what? 0. Exactly. Why? Because there is no what? There is no distance. All right. So now let's take moment about point C. So sorry if we are doing this, we are not going to be looking at summation of moment here. We are just going to look at. Let's remove this summation of moment. Don't worry. There's a case whereby we'll look at summation of moment. It is possible for us to have two moments acting at a point. Don't worry, we are going to solve series of problems up to the level that you don't expect. We are going to break them down for us. At least be expecting nothing less than 30 examples on these questions. And we are going to touch both gates, both various universities, Cambridge, and so on and so forth for us. All right. So now, if you want to take moment about point C, we are going to say moment about point C, bending moment rather. Bending moment about point C will be equals to, all right, So the bending moment about point C now, I'm going to start at this point first. Then the first question I'm going to add myself is, if I look at the right hand side, how many force do I have? I only have this force. So when you are dealing with bending moment, you don't consider the force acting at that what? At that point. Is that clear? So now we only have one force. So now, and what is the distance? The distance range from this point to this point. Of course, if this load is acting at the center, so the center here, it means we are going to have this point to this point to be L over 2, and this point to this point to be what? L over 2. Because L over 2 plus L over 2 is going to give us what? The total length of the span of this beam. Alright, so now, it means here, if I want to calculate my what? My bending moment about this point, I'm going to stand there and I'm having an upward force. Don't forget, an upward force from our condition is what? Positive. And here again, we are having an anti-clockwise moment. So it means our anti-clockwise moment here is going to be taken as what? Positive. So it means that here we are going to have RB, positive RB, multiplied by what? Multiplied by the distance, which is what? L all over what? L all over 2. Is that clear? Alright. So now let's take the moment about point A. The bending moment about point A. Alright, bending moment about point A. If I start at point A, how many force do I have? I have this and this. We are not going to consider this. Do you understand? Alright. So now we are going to say R will be multiplied by the total distance now. The distance from here to this point is what? L. So we are going to have positive RB multiplied by what? L minus what? Minus W multiplied by what? L over what? Over 2. So this is how we are going to calculate our bending moment on this what? On this beam. I hope this concept is clear to us. Please, if you have any question, you can drop in the comment section. I'm going to reply back. All right. Now, the next thing you also need to note here is this. I'm going to tell us some important points that we need to know. All right. Important points. All right. So the first thing you need to note is this. The first thing you need to know that the bending moment at the end of a simple supported beam is what? Is 0. Bending moment at the end of a simply supported beam is 0. Alright, so it means if I have a simple supported beam like this type, if I want to calculate my bending moment, I don't need to go through this process. I only need to calculate for one. I know the bending moment at point B is what? 0. The bending moment at point A is 0. I only calculate the bending moment at point what? Point C. Alright, that is just this. Alright, another point you need to note is this. That the bending moment at the free end of a cantilever beam is also what? 0. Bending moment at the free end of a cantilever is 0. Alright, you know how a cantilever is. We have a cantilever like this, and let's say we have a force here. Let's say this is A and this is B. So the bending moment at this free end, let me not put force. Let's just put something like this. So the bending moment at this free end is going to be equals to what? It's going to be equals to 0. Alright, so this is a cantilever. A cantilever is a beam that is fixed at one end and free at the what? At the other end. And if you want to draw the free body diagram of this fixed end of a cantilever, how do you do that? You should know that this is a fixed support, and this fixed support does not allow movement in both x and y direction. So we are going to have reaction in both x and y direction plus a what and a what and a moment. Is that clear? And does not allow rotation. All right. So we are going to have this. We are going to have this as our all right. So we are going to have this as arrow a y, and here as arrow a s, and here as MA. All right, so this will be the free body diagram of this fixed support. All right, so another thing you need to take note is this, that if you want to draw your shear force diagram and bending moment diagram, you are going to take note of this point, that the first thing we draw first is our what? We draw our the beam, the given beam, then followed by the what? Followed by the shear force diagram, then followed by the what? Bending moment diagram. Please take note of that. The given beam, then followed by what? Followed by the shear force diagram, and followed by the what? The bending moment diagram. All right. So another point you need to note is this. All right, shear force diagram. All right. So another point you need to note is this. If you want to draw your shear force and bending moment diagram, the length of the shear force and the bending moment diagram must be equal to the length of the given beam, that is the span of the given beam. All right. So the length of the shear force diagram and bending moment diagram must be equal to the span of the given beam. All right, so I'm going to continue with this. I'm going to clean this side. All right, another point we need to take note of this is this. I want you to note that we are going to consider various cases of this shear force and bending moments. And it is not only a simple supported beam that we have. You know, we can have a beam that is loaded with just a point load only. We can also have a beam that is loaded with uniform distributed load only. We can have a beam that is loaded with a varying distributed load only. Then we can have a beam that is loaded with a point load and a uniform distributed load and a moment sometimes. So we can have any type of beam. We can have an overhanging beam. Is that clear? So that is what makes this next point vital. So while drawing our shear force and bending moment diagram, if we have a point load on the beam, our shear force diagram, if you want to draw our shear force diagram, we are just going to be representing it with a straight line, and any point between 2 points that there is no load at all, we are going to use a constant line to represent that. All right, this is what I meant. Let's say we have a beam like this. All right, let's say we have a beam here, we have a load here, we have another load here. So if we are to draw the shear force of this beam, it's going to be like this. It's going to be like this. So let's assume that this is the 2 points I was saying, this point and this point, that there is no load. And let's assume that the shear force at this point is, let's say, 20. So you are going to have a dotted line. We are just going to trace 20 upward. We are going to trace 20 upward. Then because there is no load between these 2 points, we are going to make use of a constant line till we get to this point. Do you understand? Then we'll now check for the shear force on this point. If it is negative, then we'll go down. Then we because there is no loop between these 2 points again, we draw a straight line. You understand? Then again, we check for the shear force of this on this point here. If it is positive, we go up. Is that clear? So this is how we just draw. I'm just trying to sketch to explain the point I said earlier. Alright, now for the case whereby we now have a uniformly distributed load on this, or uniformly distributed load or a vane distributed load, we are not going to be using the point that we have a uniform. Let's say we have a uniform distributed load here. We have a uniform distributed load, so we are not going to use a straight line. Is that clear? We are going to be using an inclined line. We are going to be using an inclined line. Let's say we want to calculate let's remove this one here. Let's say this is point B, this is point C. So if we want to calculate the shear force on at point B, let's say the shear force at point B is 20 and the shear force at point C is 0. So ours is just to come to point 0 here, then we draw an inclined line to point 20 on this part. Is that clear? So if we want to draw the bending moment diagram of this uniform distributed load, we are going to be using what? A parabola, a parabolic curve. Do you understand? To represent this. But for our point load, and everywhere we have a constant line, we are going to be using an inclined line to represent that in our bending moment diagram. I don't want this video to be lengthy than this, so we are going to be stopping here. So stay tuned for more numericals on what bending moment and shear force, so that we enhance all these points I'm trying to buttress here. So thank you for watching.